Hello students, I hope all of you are doing well. So in this video we will be discussing, we will be revising moving charges and magnetism. All these topics are there. So basically in this chapter we will be focusing on your magnetic force on a charged particle and magnetic force on current carrying wire, right? So first topic that we are starting with is electromagnetic force on charged particles. So EM force, electromagnetic force, electromagnetic force. What is electromagnetic force? How much electromagnetic force? So if in a region your magnetic field and electric field both are present and a charged particle q moves with a velocity of v, then the net force on it is given by force net is equals to q into e plus q into v cross b, right? This is your electromagnetic force. This is the summation of electric force and magnetic force. This component is our electric force. Electric force is q into e, magnetic force is q v cross b. Now so this is our force, fine. The point that we need to keep in mind is that as you can notice, this are your velocity. These are dependent on velocity. Therefore, your electric force and magnetic force are frame dependent. These are frame dependent, right? Whereas this one is frame independent. The net force is frame independent. From where we are looking at, from where we are observing the motion, that will affect your electric force, that will affect your magnetic force, whereas net force is frame independent. Okay, fine. So this is about your first electromagnetic force. In this chapter our focus is more on this. In this chapter our focus is on q v cross b, magnetic force on a moving charged particle. This is something QE, that is your electric force, we have discussed in our electrostats chapter, right? Over here our focus is on this. So let us take a look at it further. So magnetic force on charged particle. Next, if we see second point, magnetic force on charged particle. What is the magnitude? Magnetic force magnitude on a charged particle is, force magnetic is QV cross B, QV cross B. This I can also write it as QVB sine theta, where theta will be angle between velocity and magnetic field. This is our magnetic force on moving charged particle, right? Magnitude, okay. Force is a vector quantity. What will be the direction? Direction will be given by right hand thumb rule. It will be given by right hand thumb rule. Now there are many ways of finding out the direction of magnetic force. Any one of them you can choose. What I prefer is, I do it your right hand thumb rule for cross product. What is that? V cross B. For example, if I take an example, let's suppose a charged particle q is there. It is having velocity in x direction and your magnetic field is at certain angle theta, right, in xy plane only. Then how we apply right hand thumb rule for cross product? Keep your fingers straight, fingers along the first vector means velocity, and turn it towards second vector b along the smaller angle, right, v cross b. The thumb will give us direction of magnetic force. Where it is coming? It is coming in this case outward direction. That means dot circle, right? This is your outward direction. So this is how we give direction of magnetic force. Just one point we need to be careful is that because force magnetic is q and q charge we know has positive and negative. If you have positive charge, so for positive charge along v cross b, that means for positive charge direction will be along v cross b only. V cross b, if let's suppose your proton is there, proton is our positive charge plus e, so v cross b outward it will come, right? But if we have a negative charge, for negative charge it will be opposite to v cross b, opposite to v cross b. How to do it? So let's suppose that we have electron. Same situation I am taking over here. Electron is there, velocity is this, and magnetic field is this at an angle of theta. How we will do it? Keep your fingers along the first vector, turn it towards second vector along smaller angle. Thumb will give you direction of force, but this is negative charge, therefore what we'll do? Opposite. So V cross B opposite, I will turn my thumb by 180 degrees, right? That means it is coming inward direction. So in this case, it is inward direction, right? This is magnitude of magnetic force. This is direction of magnetic force. Certain more points that we can understand is that force magnetic is coming due to your cross product of velocity and magnetic field. That implies this force magnetic will always be perpendicular to velocity and magnetic field also. So as force magnetic is always perpendicular to velocity, we can say that it will not do any work on it. So work done by magnetic force is 0. So work done is 0. Work done by magnetic force is always 0 because it is always perpendicular to velocity. Second point, as it is always perpendicular to velocity, it will not change the speed. That means magnitude of velocity will not change. Direction will change, but your speed remains same. Speed remain same. And if speed will remain same, that means kinetic energy also remains same. So kinetic energy same, right? So all these points are there. Your electromagnetic force, the summation of electric force and magnetic force. And acha, one point over here I would like to add, this net force is termed as Lorentz force. This net force is termed as your Lorentz force. The summation of electric and magnetic is Lorentz force. Fine, right? Then our focus in this chapter is about your magnetic force. Magnetic force Q V cross B. Magnitude is Q V cross B, which we can write Q V B sine theta. Direction is given by your right hand thumb rule. Right hand thumb rule, I have explained how to do it. V cross B, right? If it is positive charge, it will be along V cross B. If it is negative charge, we will have to turn our thumb by 180 degrees. Next, last, some more points regarding this. This force is always perpendicular to velocity as well as magnetic field. And if force is perpendicular to velocity, work done by magnetic force will be 0 and speed and kinetic energy will remain same for the charge particle, right? Let us move ahead. Yes. So students, we have discussed the first two topics, that is electromagnetic force on charge and your magnetic force on charge particle. Now magnetic force on a charge particle, how much we saw? Magnetic force on charge particle is QVB sine theta, right? This is the magnitude of magnetic force. Now depending on the angle between your velocity and magnetic field, depending on the angle between your velocity and magnetic field, the charge particle can have different types of motion. For example, you have first category, broadly we classify them three types of motion it can have. The first one is when velocity is parallel or anti-parallel to magnetic field. That means theta value will be 0 degrees or 180 degree. I have taken an example. Let's suppose magnetic field is horizontal, positive x direction. Your charge is also moving. A q charge is moving with velocity v. Angle between your velocity and magnetic field is 0 degree. If angle is 0, sine 0, 0, that implies your force magnetic will be 0. Force magnetic, whenever charge particle is moving parallel or even anti-parallel, because anti-parallel sine will be 180, sine 180, 0. So force magnetic will be 0. If force magnetic is 0, what will be the path of charge particle? Path will be straight line. So it will move in straight line motion, right? And there will be no magnetic force and the particle will either, it will continue to move with same speed in this direction in straight line path, right? Okay, moving ahead. Next is when velocity is perpendicular to magnetic field. Very important case. That is when angle is 90 degree. See over here the example that I have taken over here. Magnetic field in this case B I have shown by cross. That means it is in uniform magnetic field which is in inward direction. It is into the plane. And a charge particle Q is going with a velocity of V. We know force magnetic, if theta is 90 degree, that means force magnetic will be QVB. Right, sine 90, 1, so force magnetic will be QVB. Now, what is direction of this QVB? Let us see. We'll keep our fingers along velocity and turn it towards magnetic field. V cross B, thumb is pointing upward. Now, we know that force magnetic is always perpendicular to velocity. If force magnetic is always perpendicular to velocity, it will result into a circular motion. Force magnetic QVB, and it will be a circular motion. Particle will perform circular motion. As your force is always perpendicular to velocity, your particle will perform circular motion. Which force is providing the necessary centripetal force? Magnetic force is providing. So let us see, QVB is equals to mv square by r. When we solve it, over here v and v cancel out. R value, the radius of the circular path, the radius of this circular path can be given as mv by qb. mv by qb will be the radius of the circular path of a charged particle q moving in a magnetic field B with velocity v, right? This mv by qb, as we know that radius is mv, coming m into v is what? Your momentum. Momentum can also be written in terms of kinetic energy. What can I write? It is root over 2 mk by qb. So radius mv by qb, we can keep result in terms of kinetic energy. K is kinetic energy, right? Also, one more result that we can keep in mind is, because in many questions this point comes, if let's suppose a charged particle is accelerated through a potential difference of v. If a charged particle is accelerated through a potential difference of v, then it acquires the kinetic energy of q into v. Q into v. If a charged particle q is accelerated through potential difference v, then the kinetic energy attained by it is q into v. Therefore, over here in place of k, we can write in terms of potential difference, which will come out to be root over 2m q into v. This v is the potential difference. So, by qb. Three results have come for your radius, right? mv by qb in terms of kinetic energy, in terms of potential difference. Fine. So, this is our radius relation. Path will be circular motion, right? Now, if radius is mv by qb, another result that we need to know over here is about your time period. Is it visible here? No, I'll write over here. See here, time period. What can I write? Time period, right? Time period, we can write it as your basically 2 pi r by v. Radius we have got it as mv by qb. When we substitute all of this, your time period result will come 2 pi m by qb. This is your time period result. From this frequency we can write, frequency is basically what? 1 by t. So frequency will be qb by 2 pi m. Also we can write down your angular velocity. What will be your angular velocity? Omega is equals to, this is t is 2 pi by omega, so omega can be written as qb by m. These are your results, right? Quickly I will summarize it. So whenever particle is having velocity parallel or anti-parallel to magnetic field, force is 0 and the path is straight line motion. Next, when velocity is perpendicular to magnetic field, that is angle is 90 degree, the motion is circular motion and the radius of that circular path is mv by qb in terms of kinetic energy, in terms of potential difference. Fine. The time period of this circular motion, the time period of this circular path is 2 pi m by qb. Point to be noted over here, that time period does not depend on velocity. Time period is independent of velocity, right? So two charged particle having same mass, having same charge, and you are moving in the same magnetic field with different velocity will also take same time period, right? So time period is independent of velocity. Fine. Frequency you can write and your omega you can write it, right? So these are the two cases. The third case is when your velocity is at certain angle to magnetic field. We'll see that also. So we have discussed two cases. Now the third case, when velocity and magnetic field are at an angle theta, this angle theta is other than 0, 180 and 90 degree. Let us consider the situation. Let's say that you have magnetic field B in horizontal direction and a charged particle Q is having a velocity V such that this is at an angle of theta with the magnetic field, right? Now what will happen? Over here the condition is that this theta is other than 0, 180 and 90, because for all these we have already seen the cases, right? Now this, when velocity is at certain angle theta, this velocity will have two components. The first is along the magnetic field. This is our magnetic field. One component will be along the magnetic field, which is V cos theta, and this component will be your V sin theta perpendicular to magnetic field. Over here, there will be no force acting due to your V cos theta. Magnetic force will not be there due to your V cos theta. But V sin theta, which is perpendicular to your magnetic field V sin theta. Due to that, force magnetic will come in this. How much will be our force magnetic? The force magnetic will be QVB sin theta. Now see over here. Due to this V cos theta, the charge particle continues to move in straight line. And due to this force QVB sin theta, let us see the direction of V sin theta B. So V cross B, this is how we do it, V cross B. Now when we do V cross B, it is coming, thumb is inward. That means this, due to this V sin theta, the charge particle will move in circular path. Due to V sin theta, it is moving in circular path, and due to V cos theta, it is dragging. It is dragging, or it is moving in straight path. As a result of these two, the resultant motion will be something like this. Sorry. This will be your resultant motion. This motion, this path is termed as your helical path. Helical path. When charge particle is moving at an angle theta other than 0, 90, 180, then the motion of particle will be helical path. Due to V cos theta, it will move in straight path. Due to V sin theta, it will have circular motion. Combined, the effect of this will be your helical path. Now, certain points regarding this. What will be the radius of these circular paths over here? Radius of the circular paths will be, R will be equals to mv perpendicular. In this case, V perpendicular is your, you can write V perpendicular by QB. Again, how we are deriving it, this force is responsible for your centripetal force. So QVB sin theta is equals to mv square by R. From that we'll get, so this over here I can also write mv sin theta by QB. Well and good. Time period. How much is the time period of this circular motion? Time period will be 2 pi m by QB. As we have already seen, time period does not depend on velocity, so it will be 2 pi m by QB itself, right? So these are the two results that we have got for this third case. Apart from this, one more point that we should remember is there is something known as pitch of the helical path. Pitch of helical path. What do we mean by pitch? Pitch is basically the horizontal distance traveled by particle by the time it completes one revolution. Pitch is the horizontal distance traveled by the particle by the time it completes one revolution. How do we calculate? So pitch is given as, formula for pitch is horizontal distance. In horizontal, if you see, it is going with your uniform speed, V cos theta. So distance equals to speed into time. Speed is horizontal over here, V cos theta, and your time in one revolution. How much time it is taking for one revolution? 2 pi m by QB. So pitch will be 2 pi m by QB. So this is our distance traveled by the time it covers one revolution. This is our pitch, right? So all these results are there for case number 3. I hope this is clear, right? So we have done with this. Let's move ahead to the next topic. Okay. So the case that we are discussing now is, the topic we have is deflection of charge particle. So what do we mean over here? In the last topic, in case number 2, we have seen that velocity, when velocity of particle is perpendicular to magnetic field, it performs a circular motion, right? So that only we are taking it forward. So let's consider a situation that a particle having mass m, charge q, moving with velocity v, and magnetic field is perpendicular, or velocity is perpendicular to magnetic field. This magnetic field is present in a region only having this till d, right? This is the d is the distance till which your magnetic field is present. Now let's consider a situation where your d distance is less than r. What do I mean by this? That means this particle will tend to perform your circular motion. This particle will tend to perform circular motion with radius of r, but this radius is greater than this distance in which your magnetic field is present, and therefore the particle will not be able to complete the circular motion, and it will deviate out. It will move out of the magnetic field region at certain angle theta. It was going horizontally, it went out at this angle. It went out over here at an angle of theta. So this is a deviation. Deviation or deflection, and a deflection, or you can write deviation. So deviation. So what is our deviation? When the radius of the particle is more than this distance d in which your magnetic field is present. Now, if we have to find out this theta, there are two ways. One is in terms of time, another is in terms of your distances. In terms of time, if I have to write down, so this theta, in terms of time, if I have to write, in terms of time t, What do I mean by this? Let's suppose that this charged particle is taking a time t. This is theta, that means this implies this is your radius r, this will also be radius r. This is theta, that implies this will also be theta. So if it is taking time t, then theta angular displacement can be written as omega into t. What is our omega value? Omega value is qb by m. So it can be written as theta will be qb by m into t. Fine. This is one way, giving your deviation in terms of time t. Another is giving in terms of distance d and r. So in terms of d and r. How to do it? Let us see. If this angle is theta, this is theta. Now see this triangle over here. If you notice, I'll draw it over here. Right? In this triangle, if we have to write down sine theta will be your what? Opposite by hypotenuse, that is your opposite. This distance is how much? D by r. So if we substitute, r value is your how much? mv by qb. So when we substitute, we get over here qbd by mv. So sine theta in terms of distances we can write as your, or theta, the deviation will come out to be sine inverse of qbd by mv, right? So these are the results in terms of time, the deviation in terms of the distances. Fine. One last point that I want to discuss is, this is we have discussed when your d value is less than r, that means the radius is more than this distance. What if your distance d is more than your r? So if I talk about, if d is greater than r, that implies that the charged particle will get sufficient distance to complete the circular path. In this case, I am drawing it over here. So let's suppose it will be something like this. If d is greater than r, that implies the particle will be moving this way, right? So how much will be deviation in this case? It entered over here with velocity and it is exiting. It will exit with a speed of v only, and this deviation, as you can notice, deviation in this case will be your 180 degrees. Okay? It will be 180 degrees will be deviation when your d is greater than r. So this is about your deviation. These are the results. Let's move ahead. Now we will be looking at your motion of charged particle in electric field and magnetic field combined. Fine. Let's move ahead. Okay. So over here we are discussing a specific case when your velocity, magnetic field and electric field are perpendicular to each other, right? So we know one thing. First of all, how much is your electric force? Force electric is given as Q into E, right? What is your magnetic force? Magnetic force is Q V cross B. If your velocity is perpendicular to magnetic field, we can write it, it will be your QVB. Now we are over here trying to find out a specific case. What should be the velocity? What should be the velocity of a charged particle such that it goes undeviated? That means it moves in straight path only. So we know that this is your V, magnetic field is in inward direction. So V cross B, due to this inward direction, V cross B, force magnetic will come upward. How much it will be? QVB. Now how much force should act? First of all, your electric field will be in downward direction, then only we will get a downward electric force which will be equals to Q into E. If the charged particle goes undeviated, that means force should be 0, F net should be 0 on this. That implies QVB should be equals to QE, that implies QQ cancel, V value is equals to E by B. That means if your velocity, magnetic field and electric field are perpendicular to each other and the particle has a velocity of, magnitude of velocity of E by B, then the particle will move undeviated, right? So please keep this result in mind. Let's move ahead. Yeah. So up till now we have discussed your force acting on a charged particle, right? Now we are moving on to your magnetic force on current carrying wire. Let's consider a situation that a wire carrying a current I of length L is present in a magnetic field of B. Then the magnetic force on this, first of all, why magnetic force will act? If current is flowing towards right in this wire, if current is flowing like this, that means the negatively charged electrons are moving towards opposite to the current. If negatively charged electrons are moving, they will be experiencing a force, and as a result of the force experienced by the negatively charged electrons, this wire also experiences the magnetic force. The magnitude of this force is given as, magnetic force is given as IL cross B, IL cross B. This I can also write it as ILB sine theta. So the magnitude of magnetic force will be ILB sine theta. Over here, theta is basically angle between length vector and magnetic field. Length vector, what should we consider the direction of L vector? L vector direction is always considered along the direction of current, right? Okay, so this is our result. Magnitude of force on a current carrying wire, magnetic force on current carrying wire. Now if we talk about the direction part, so direction is given by RHTR, right hand thumb rule. As you can see that force magnetic is basically your cross product of length and magnetic field. So we can directly do cross product for L cross B. L direction is taken along current. So L cross B, in this specific case, L is towards positive X, B is towards negative Z. So L cross B, when we do it, your thumb is pointing upward. So force magnetic over here comes out to be right in upward direction. In this specific case that I have drawn over here, the angle between length vector and magnetic field is 90. Therefore, in this case, your force magnetic will be your simply ILB, right? Okay, moving ahead. So next that we have to discuss is your random shaped wire. Random shaped wire. Let's consider a situation that something like this wire is given to you. A random shaped wire is there, right? And through them a current I is flowing. How to do in these cases? A random shape wire, to find out your magnetic force on random shape wire, we replace this random shape wire with a straight wire joining the initial point and final point. What initial I am taking? We'll take initial in the direction of current. So over here, this is point A, this is your point B. We will replace this with a straight wire joining the two ends of the wire, this curved wire, right? This is what we have got. How much current we have to consider? Current will be going in this direction, it will be I, right? So whatever the force on this curved wire will be equal to the force experienced by this straight wire, which is joining the two ends. Some example we can consider in this. Let's suppose a semicircular wire is there. Okay, a semicircular wire of radius r through which current I is flowing. It's a curved wire. How do we find out current on a magnetic force on this? So it will be A, B, the two edges. We will join the two edges. This is R. We'll replace it with a straight wire. How much our current will be? Force magnetic is equals to ILB. Angle is 90 degree. L, how much is length over here? R plus R, 2R. So I into 2R into B. So this is how we find out your magnetic force on a random shaped wire or a curved wire. Also, one more point that we can remember is, let's suppose a circular wire is there. In case of circular wire, the magnetic force on a circular wire will be 0. The net magnetic force on a circular wire will be 0, right? From this thought only, or from this concept only, we can answer this, that the magnetic force on circular wire will be 0. Let us move ahead. Okay, so our next topic is force between parallel wires. We are talking over here magnetic force between parallel wires. Let's consider a situation, two long parallel wires separated by a distance r. Through them current is I1 and I2 is flowing, right? Same situation I have drawn here also. The difference is that in this case the current is flowing in same direction, in this case the current is flowing in opposite direction. Why magnetic force will act between them? As you can see that if current is flowing through this will be producing a magnetic field. This wire, let's say that this wire number A, wire A. So wire A will be producing magnetic field in inward direction along the length of this wire B. Due to this magnetic field, this current carrying wire will experience a magnetic force. So when we finally derive the result, the force between them comes out to be, force per unit length is mu naught I1 I2 by 2 pi r. This is the magnitude of force, and to be noted over here, this is force per unit length. On a unit length, the force between them, each one of them will apply force on each, both will apply force on each other, and that force will be mu naught I1 I2 by 2 pi r. This is the force per unit length magnitude. Then what is the difference between situation 1 and situation 2? About direction. So as you can see, this wire A will be producing magnetic field in inward direction. Due to inward direction magnetic field, on wire B, IL cross B. If we do L cross B, force is over here. Similarly, due to wire B, on A, force will be towards B wire. and therefore the force will be force on A due to B, force on B due to A. Magnitude wise it will be this only, but they will be attracting each other. What difference will come over here? Let us see, this wire, A wire, is producing magnetic field in inward direction, right? And if we do it over here, if we apply this L cross B, if we do it, so the force is coming. So this is force on B due to A, and similarly on this one it will come force on A due to B. So finally, if I have to summarize it, force between parallel wires, if two current carrying wires are there, two parallel current carrying wires are there, the force per unit length between them will be mu naught I1 I2 by 2 pi r. This is the magnitude of force. What about direction? If the current is flowing in same direction, the wires will be attracting each other. If the current is flowing in opposite direction, then the wire will be repelling each other. That means force will be opposite, right? Okay then, so this is it. Let's move to the next topic. So let us see one by one. I have put the topic, but one by one we'll see. First of all, we are talking about magnetic moment. Magnetic moment is denoted by capital M. What is magnetic moment? If let's suppose that a loop, a current carrying loop is carrying a current I, then the magnetic moment for this M vector is given as I into A vector. A vector, the area vector, right? So magnetic moment is current into area vector. Direction of magnetic moment is along the direction of area vector. Area vector direction is found out by your right hand thumb rule. We will turn our fingers along the direction of current. The thumb will give us the direction of area vector, and in turn your magnetic moment also, right? Okay, next, if I have to say, let's suppose that n turns are there. This is for one loop. If n turns are there, then magnetic moment can be written as NIA, right? This is for n turns, magnetic moment. Next, if we talk about, let's consider a situation that in a region, let's suppose a magnetic field is present B, and a loop is present, through which current I is flowing. Then it will experience a torque. The torque on the magnetic, the torque due to the magnetic force will come out to be, torque will be given as M cross B, the cross product of magnetic moment and magnetic field. Fine. Now, if we talk about your potential energy of the loop, whenever a current carrying loop is present in a magnetic field, then its potential energy denoted by U is given as M dot B minus M dot B. That means it is dot product of magnetic moment and magnetic field. Over here, some points that we should keep in mind, that let's suppose if angle between your magnetic moment and your magnetic field is 0, that means if theta is equals to 0 degree, MB cos 0, that means your U value will come out to be minus B. If theta value is 180 degrees, if theta is 180 degree, that implies your U value will be minus MB cos 180, minus minus plus, so U value will be MB. This is your minimum potential energy and this is your maximum potential energy. Minimum potential energy occurs at 0 degrees. That implies that this is your stable equilibrium. This is a condition of stable equilibrium, right? And when it is theta is 180 degrees, your potential energy is maximum. That implies this is condition of your unstable equilibrium. Okay, apart from this, what else we can find out from this relation, potential energy relation? If let's suppose a coil is turned such that initially it was making an angle theta 1 and finally it is making an angle theta 2, that means angle between your M and B initially is theta 1 and finally it is theta 2. Then the work done to turn the coil, we can write down with the help of potential energy. Work done will be U final minus U initial. U relation we have seen it, minus M dot B, and therefore we can write down over here MB cos theta 1 minus of cos theta 2. So this is the work done to rotate the coil from an angle of theta 1 to theta 2, right? So all these results are there. I hope it's okay for you. Just keep the results, the highlighted results in mind. We have discussed about your magnetic moment. Magnetic moment is given as NIA. A is the area vector, I current, N is the number of turns. Torque on a loop. Torque on a loop is given as cross product of magnetic moment and magnetic field. Okay, potential energy of loop in a magnetic field, potential energy is given as U is equals to minus M dot B, that means dot product of magnetic moment and magnetic field. Next, over here certain points we should be careful with. If your loop is placed such that the angle between your M and B is 0. That implies your potential energy will be minimum. That is the condition for stable equilibrium. If theta is 180 degrees, then your potential energy will be maximum, M into B. That implies this is the condition of unstable equilibrium. Lastly, work done. If a loop is turned such that initially angle between M and B was theta 1, finally angle between M and B is theta 2, then work done can be written as U final minus U initial. When we substitute this over here, U final minus U initial, the result we get is work done will be MB cos theta 1 minus cos theta 2. Basically, we have to find out change in potential energy, right? So with this, we have discussed all our topics of this chapter. I hope you found the video helpful. All the highlighted results, please keep them in mind and practice questions on the basis of this, right? Do consider to press the like button and subscribe to the channel. Thank you very much. Bye bye.